Hi students, and welcome to our continued discussion of relations and functions. So here we're going to use our precise definitions. So a relation, this is meaning that each element of the domain input is mapped to an element or elements of the range, which is our output. So this is our mapping. So for instance, you can have one element mapped to multiple elements or just one element mapped to one element. So that's our definition of a relation. Now a function is different. Now all functions are relations because they meet the criteria, but there's a restriction. And what it says is each element of the domain or input is mapped to exactly one element of the range or output. So in this case here, what we can see is that all functions clearly meet the definition of a relation. However, not all relations can be functions. So let's take a look at an example here. So we've got, let me just grab my little hand tool. We've got a relation, and here's our rule for mapping. We're told that y, the output, or our dependent variable, is equal to x squared plus 1, where x is our input or our independent variable. So let's go ahead and do this mapping here. So I'm going to grab a red pen. So let's see, if I put in 1, so substituting 1 in for x, well 1 squared is 1, and 1 plus 1 is 2. So 1 gets mapped to 2 and to only to 2. So what does 2 get mapped to? Well, 2 squared is 4, plus 1 is 5. So 2 is going to be mapped to 5. I'm just going to put little arrows on here. Hopefully that doesn't look too messy. And for 3 now, well, 3 squared is 9, plus 1 is 10. So 3 gets mapped to 10. And here, 4 squared is 16, plus 1 is 17. And this just follows the rules of BEDMAS that we've been doing for quite some years now. So our question is this relation a function? Well, we can see for this specific case of our domain being 1, 2, 3, and 4, we can see that each individual element is only mapped to a single output. So this means that, yes, indeed, this is, sorry, just trying to find my little pen guy here, hard to see with the red. So this is a function because it meets our strict definition. So recall that the definition says that each element of the domain is mapped to exactly 1, and that's exactly what we're seeing here. So let's take a look at another example. So in this case, our rule is x is the square of y. X being our input or our independent variable, and y being our output or our dependent variable. And we're asking, is this relation a function? So we can go through this by going our mapping route. So let's take a look here, grabbing a pen. So x is the square of y. Well, 1 is definitely the square of 1, but 1 is also the square of negative 1. 4 is the square of 2, but 4 is also the square of negative 2. 9 is the square of 3, but 9 is also the square of negative 3. So let's take a look. Is this relation a function? Well, it's definitely a relation because it has a mapping of each element in the domain. And now this is not a function because each input has more than one output being mapped to it. So what we can say here is, grabbing a little pen, is this is not a function. And your reason is simply more than one output for an input. Now remember, if you had, for instance, a whole bunch of inputs that were just, they all had one output, and even just one input with 2 outputs makes the entire relation not a function. So we only need one case. Here we have 3 different cases of double mapping, and only one case of double mapping is needed to declare it not a function. So this definitely is not a function. So let's take a look at our next. So here we're asked, does this set of ordered pairs represent a function? So we got the ordered pairs, x comma y, 3 comma 2, 4 comma 7, 5 comma 5, 6 comma 2. So remember, what's really important here is that your x value always represents your input, and your y value, this is your output. So what we want to do is, what can be helpful here is let's make a list of what we have. So for instance, if I make my x, y chart here, so when x is 3, y is 2. When x is 4, y is 7. And when x is 5, y is 5. And when x is 6, y is 2. So we don't have any of the x values being repeated, and each individual x value is only mapped to a single y value. So this is a function. So now what we can ask is what ordered pair could be added to the set so it's no longer a function. So for instance, I can add an ordered pair to this set of numbers to make this no longer meet the requirements of a function. So for instance, all I have to do is add another input that we've already used, but give it a different output. So for instance, I could give it a 3 to something else than a 2, have 4 being mapped to something else than a 7, have 5 being mapped to something else than a 5, or have a 6 being mapped to something else than a 2. Well, I like the number 6 because it's the first perfect number. So let's say that I add 6 comma 3. So what this would do is this would add to our chart 6 and 3, and now 6 gets mapped to both 2 and 6 gets mapped to 3. So anytime when you're taking a look at a set of ordered pairs, if you have an x value that shows up multiple times and is mapped to more than one consistent value, then it cannot be a function. So there's our examples.